So in this section, we get into the meat of how the nephron works. The kidneys are going to convert blood plasma into urine in 3 different stages. These are the topics of the rest of this chapter. We'll begin here with glomerular filtration, then tubular reabsorption and secretion, and the third and final phase is water conservation. Glomerular filtration happens here in the glomerulus. Then we have this tubule. We have the proximal convoluted, the nephron loop, and the distal convoluted tubule. This is where we're going to see removal of the useful solutes from the filtrate and returning them to the blood, as well as tubular secretion, which is where we're going to remove additional wastes from the blood and put them into the filtration. So reabsorption is pulling stuff back into the body, and secretion is pushing additional stuff out into the filtrate or the urine. The third phase is where we see water conservation. This is where we remove most of the water from the urine and return it to the blood so that we concentrate the waste products. Now, we have specific names for each of the fluids as they pass through the tubule and change. The glomerular filtrate is the filtrate that comes initially from the glomerulus. It's the fluid in the capsular space. Nothing has happened to it yet. There's little protein in it because the protein can't pass through the pores, and there's still a fair amount of water as well as materials that we will need to reabsorb. The tubular fluid is the fluid that we find in the renal tubule, in the proximal convoluted and the distal convoluted tubules, as well as in the nephron loop. It's similar to the glomerular filtrate, except the tubular cells have removed and added different substances. Now, we don't call it urine until it enters the collecting duct, where the only remaining change is water content. No more substances will be absorbed or secreted. So in the first phase, we look at glomerular filtration. Let's review the structure of the glomerulus. Remember, we have this big capillary bed, and in it we have the efferent and afferent arterioles. The afferent arteriole is bringing blood into the glomerulus, and the efferent is taking blood away. All around the vessels of the glomerulus, remember we had these podocyte cells. They have a cell body and lots of little foot processes. These foot processes pretty much cover the whole vessel, and they are separated by these narrow slits called filtration slits. This is the filtration membrane, where we see the capillary here on the left side and the filtrate here on the right side of the figure. Glomerular filtration is a special case of capillary fluid exchange process that we examined earlier in the semester. In this case, water and some solutes in the blood plasma will pass from the capillaries of the glomerulus into the capsular space of the nephron. There are 3 barriers involved in this filtration membrane. We have the fenestrated endothelium of the glomerular capillaries. Glomerular capillaries exhibit this fenestration, which allows the passage of much more material through the membrane. The filtration pores are about 70 to 90 nanometers. Even though these fenestrations in the capillaries are quite large, the basement membrane prevents their passage, as well as the filtration slits on the other side. So the basement membrane is a proteoglycan gel. It's got a very negative charge, and so it excludes the molecules greater than 8 nanometers. Albumin is repelled because it has a negative charge. Blood plasma is 7% protein, and the filtrate is only 0.03% protein. So just a very little bit of protein is making it through. This basement membrane is sort of like a sponge, and so it's almost like pushing sand through a sponge. Like some of the sand might get through and make it over to the other side, but most of it will be returned to its origin. So on the other side of the basement membrane is where we see the filtration slits that are created by the podocytes. Remember, they have the cell extensions or pedicels that wrap around the capillaries and form a barrier layer. These filtration slits are about 30 nanometers wide. They're negatively charged, which is what presents an additional obstacle for these large anions. So in this figure, we can see the things that actually pass through the filter and make it into the capsular space, and then the things that get turned back. The blood cells are too large to pass through the fenestrations. Plasma proteins are also very large. Large anions will get turned back because of the negative charge. Minerals and hormones that are bound to proteins are simply too large to pass through. However, we do see that water, electrolytes, glucose, amino acids, fatty acids, vitamins, urea, uric acid, and creatinine all pass through into the glomerular filtrate. Almost any molecule smaller than 3 nanometers can just pass freely through the filtration membrane. That includes this large list, majority of the things that pass through. Some substances have a low molecular weight and are bound to plasma proteins. These are things like thyroid hormone, calcium, iron, and so they're held in the blood by these binding proteins. This is one of the reasons that binding proteins are so important. Any of these materials that are unbound will pass freely into the filtrate because by themselves they're fairly small. Anything that can cause damage to the filtration membrane will allow albumin or blood cells to filter through. Kidney infections can cause damage to the filtration membrane as well as trauma to the kidneys. Proteinuria is when we see protein in the urine, and this is a condition that might indicate that there's some infection or trauma in the kidney. Hematuria is the presence of blood in the urine. Often distance runners and swimmers experience temporary proteinuria or hematuria. This is due to prolonged strenuous exercise. They experience these symptoms because, as you know, during exercise, we're predominantly using the fight or flight mechanisms in which blood flow is slowed down to the kidneys and directed more towards the muscles. During prolonged and strenuous exercise, this means that the kidney could go without a good blood supply for an extended period of time. This reduced perfusion causes the glomerulus to deteriorate because it's simply not getting enough oxygen to keep the tissues alive. Okay, so here we go. It's time to talk about filtration pressures again. We're going to deal with hydrostatic pressure and colloid osmotic pressure. Now, you already have a good understanding of that from the previous chapter. So let's understand that blood hydrostatic pressure is much higher in the glomerular capillaries than it is in most other capillaries. It's 60 millimeters of mercury compared to 10 to 15 that we see in other capillaries. The reason for this is explained by the variation in size between the afferent arteriole and the efferent arteriole. The afferent arteriole is much larger than the efferent arteriole. So there's a larger inlet and a smaller outlet. That means lots of blood is being pushed in here and less flow is allowed out. This is sort of like coming into a merging of lanes on a road. You've got 2 lanes and traffic is flowing along nicely. And then there's some congestion and only 1 lane leaving town. So there's a lot more pressure in the glomerular capillaries than there is on the other side. The hydrostatic pressure in the capsular space is about 18 millimeters of mercury. This is due purely to the high filtration rate and continual accumulation of fluid in this capsule outside of the capillary bed. Now, the colloid osmotic pressure of the blood is about the same as it is elsewhere, 32 millimeters of mercury. The glomerular filtrate is almost protein-free, and so it has no significant colloid osmotic pressure. So we have a high outward pressure of 60 millimeters of mercury, which is opposed by the colloid osmotic pressure, drawing water in because the capillary blood has more particulate in it, and the filtrate virtually has none. And then 18 in because of the capsular pressure. So 18 millimeters of mercury pressing in, 60 millimeters of mercury pressing out. That's simply the hydrostatic pressures. And then a colloid pressure drawing fluid back in towards the capillaries because of all the particulates in the blood that are not in the filtrate. So we see a net filtration pressure of 10 millimeters of mercury. Thus, this is the rate of filtration out of each Bowman's capsule. The high blood pressure in the glomeruli makes the kidneys especially vulnerable to hypertension. This can have devastating effects on renal function. Hypertension can rupture the glomerular capillaries and lead to scarring of the kidneys, which is called nephrosclerosis, as well as atherosclerosis in the renal blood vessels, which ultimately leads to renal failure. So renal failure is one of the primary risks of high blood pressure. So this would be a great time to pull out a pen and paper, pause the recording, and diagram the glomerulus, including the 3 layers of the filtration membrane, as well as the filtration pressures and the components that contribute to the filtration pressure. Once you've spent some time putting pen on paper, all of this should become really clear. This is really cool stuff, I think. So take the time right now and do it. So the glomerular filtration rate is the amount of filtrate that's formed per minute by the 2 kidneys combined. It equals the net filtration pressure multiplied by a filtration coefficient that depends primarily on the surface area of the filtration barrier. That usually means about 125 milliliters per minute, or 180 liters per day in a male, and 150 liters per day in the female. The reason for this difference is the filtration barrier is about 10% smaller in females than it is in males on average. The total amount of filtrate that's produced equals 50 to 60 times the amount of blood in the body. 99% of this filtrate is going to be reabsorbed, since only 1 to 2 liters of urine are excreted per day. Imagine if that wasn't the case, and we produced 150 to 180 liters of urine a day. Wow, we would be in the bathroom all day. If GFR is too high, fluid flows through the renal tubules too rapidly for them to reabsorb the usual amount of water and solutes, and urine output would rise. This would result in a risk of dehydration as well as electrolyte depletion. If the GFR is too low, then we'll see that many wastes are reabsorbed and azotemia may occur. That is, there would be too many nitrogenous wastes left in the blood. GFR is controlled by adjusting the glomerular blood pressure from moment to moment. It's achieved by 3 homeostatic mechanisms. There's renal autoregulation, in which the kidney regulates its own GFR. There's sympathetic control, as well as some hormonal control. We'll investigate each of these. In renal autoregulation, the nephrons adjust their own blood flow, and thus GFR, without any external nervous or hormonal control. This enables them to maintain a relatively stable glomerular filtration rate, in spite of changes in systemic and arterial blood pressure. There are 2 methods, the myogenic mechanism and the tubuloglomerular feedback mechanism. This renal autoregulation is really important. It would only take the mean arterial pressure rising from 100 to 125 millimeters of mercury and urine output would increase from the normal 1 to 2 liters today to about 45 liters per day. The myogenic mechanism is based on the tendency of smooth muscle to contract when it stretches. So an increase in arterial pressure. So an increase in arterial blood pressure would stretch the afferent arteriole, and the arteriole would constrict against that pressure and prevent blood flow into the glomerulus from changing much at all. When the blood pressure falls again, the afferent arteriole would relax, and this allows blood to flow more easily into the glomerulus. In this way, the filtration rate will remain fairly stable. The mechanism of tubuloglomerular feedback is a little bit more complex and less well understood. But here, the glomerulus receives feedback on the status of the downstream tubular fluid, that is, in the kidney tubule, and adjusts the filtration rate to regulate the composition of the fluid, stabilizes its own performance, and compensates for fluctuation in systemic pressure. This feedback mechanism is taken care of by what we call the juxtaglomerular apparatus. This is a complex structure that's found at the very end of the nephron loop, where it has just re-entered the renal cortex. Here, the loop comes into contact with both the afferent and efferent arterioles at the vascular pole of the renal corpuscle. There are 3 specialized kind of cells that occur in this juxtaglomerular apparatus: the macula densa, the juxtaglomerular cells, or the JG cells, and the mesangial cells. The macula densa, you can see right here, is a patch of slender, closely spaced epithelial cells that are at the end of the nephron loop, on the side of the tubules that face the arterioles. So they're in contact with the arterioles. These sense variations in flow or fluid composition and secrete paracrine signals that stimulate the juxtaglomerular cells. The juxtaglomerular cells are enlarged smooth muscle cells. These are the green cells that you see here. They are on the afferent arteriole directly across from the macula densa, and to a lesser extent on the efferent arteriole. When they're stimulated by the paracrine secretions of the macula densa, they can either constrict or they can relax, thus increasing or decreasing blood flow into the glomerulus. They also contain granules of renin, which they can secrete in response to a drop in blood pressure. This turns on the Renin-Angiotensin-Aldosterone Mechanism, which we'll look at here shortly, that acts to rise blood pressure. The mesangial cells are in a cleft between the afferent and efferent arterioles right here, as well as among the capillaries of the glomerulus. They're connected to the macula densa and the juxtaglomerular cells by means of gap junctions, and they also communicate by means of paracrine secretions. It's thought that they're involved in constricting and relaxing the capillaries to regulate the flow through the glomerulus. They can constrict the glomerular capillaries and limit flow, as well as communicate with the juxtaglomerular cells and cause them to constrict. They're also involved in building a supportive matrix around the glomerulus, and in addition have been seen to phagocytose any debris in the area. Again, the mechanism of their action is not very well understood at this point. Although the details of tubuloglomerular feedback are still not that well understood, it is known that if GFR rises, the flow of tubular fluid increases. More sodium chloride is reabsorbed. The macula densa stimulates the juxtaglomerular cells with some kind of paracrine secretion, and those cells contract, which constricts the afferent arteriole, thus reducing the GFR Or we might see that the mesangial cells constrict and constrict the capillaries here and reduce filtration in the glomerulus. We also know that if GFR falls, the macula densa cells have another paracrine secretion that causes the afferent arterioles to relax and the mesangial cells to relax, thus increasing the glomerular filtration rate by allowing an increased blood flow. These mechanisms of autoregulation maintain a dynamic equilibrium. GFR fluctuates very little with a substantial change in blood pressure. Renal autoregulation, however, cannot compensate for extreme blood pressure variation. When mean arterial pressure maintains itself between 90 and 180 millimeters of mercury, the GFR remains pretty stable. However, once we get below 70 millimeters of mercury or above 180, we see some extreme effects. For example, below 70, glomerular filtration and urine output will cease. We see this occur during hypovolemic shock. This is why kidney damage is such a high risk when someone is in hypovolemic shock. Okay, so yet another opportunity for a diagram. Now it's time to diagram the juxtaglomerular apparatus. Identify each of the 3 types of cells involved and what their roles are. Just take a few minutes, do it now, and it'll all be much more clear. The renal blood vessels are richly innervated with sympathetic nerve fibers. The sympathetic nervous system and adrenal epinephrine act to constrict the afferent arterioles. As you'll recall, during strenuous exercise or in acute conditions like circulatory shock, this sympathetic system acts to reduce GFR as well as urine output. It redirects blood from the kidneys to the heart, brain, and skeletal muscles. In this case, GFR may be as low as a few milliliters per minute. When blood pressure drops due to blood loss or other causes, the sympathetic renal nerves stimulate the juxtaglomerular cells. As we've already learned, they secrete the enzyme renin. Renin, secreted from the kidneys, acts to convert an enzyme angiotensinogen into angiotensin 1. In the lungs and the kidneys, ACE, or angiotensin converting enzyme, will convert angiotensin 1 into angiotensin 2. Angiotensin 2 is the active hormone, and it works in several different ways to restore fluid volume as well as blood pressure. Angiotensin 2 is a potent vasoconstrictor, so it raises blood pressure throughout the body. It does this by constricting the efferent arteriole and raising GFR despite very low blood pressure. It also lowers blood pressure in the peritubular capillaries, which enhances the reabsorption of sodium and water. Thus, we retain more sodium and water in the presence of angiotensin 2. It also stimulates the adrenal cortex to secrete aldosterone. This promotes sodium and water reabsorption in the distal convoluted tube. This promotes sodium and water reabsorption in the distal convoluted tubule as well as in the collecting duct. It stimulates the posterior pituitary to secrete antidiuretic hormone. This promotes water reabsorption by the collecting duct. Finally, angiotensin 2 also stimulates thirst and thus water intake. So its primary function is to increase fluid volume as well as blood pressure. So this brings us to the end of this section on urine formation from the glomerular filtration perspective. Next, we'll move on to the tubular reabsorption and secretion phase of urine formation.